All right, here we are at the Gram-Schmidt process. So what we're going to do is we're going to go through and produce an orthogonal basis, and then we'll take the extra step and make it orthonormal, which you remember just means make it of length 1. So if I have two vectors and they are not orthogonal, right? I think you can probably see that. If you take the dot product, they are not orthogonal. They are a basis, and so I want to make an orthogonal basis. So what I'm going to be doing is I'm going to be finding the projection and then finding that z vector, right? So that's going to be orthogonal. So if I'm going to just let the first vector in my orthogonal basis be the first one. Done. Okay, so now go find my second vector v2, which will be in the orthogonal basis, and what it's going to be is going to be that z, and so that's going to be the y minus the y hat, and where y hat I'm just going to call it as p, and oops, I meant to multiply this by x1, right, times the vector x1. Okay, so you know what the projection is, right? This is just like saying z here. So here we go. So to find the v2, or the z, it's y minus y hat, right? So let's go do it. So v2 is the vector that's going to be x2, 1, 2, 2. Subtract off, so I'm going to be dotting x2 with x1. So 1, 2, 2, dotted with 3, 6, 0, all over, and I'm going to be dotting x1 with itself. So 3, 6, 0, and then multiply that times the vector x1. Okay, so this is 1, 2, 2 minus, so let's go through here. I get 3. I'm going to make sure I keep the parentheses out here, right? This is minus out here. So I get a positive 3, a positive 12, and a 0, right? All over a 9 plus a 36, all times my 3, 6, 0. So I get this 1, 2, 2 minus, so this gives me a 15 over a 45 times a 3, 6, 0. So that's 1, 2, 2. So this gives me a 1/3, right? So I'm going to multiply the 1/3 in. So I get a minus, a 1, a 2, and a 0. So this vector turns out to be 0, 0, 2. So my ortho, okay, so this my orthogonal basis, my orthogonal, I missed a syllable in there, right? Basis will be v1, which is 3, 6, 0, comma, 0, 0, 2. And let's just check. If I take the dot product of this, it is 0, right? So the dot product is 0. That means they're orthogonal to each other. All right. So now I've got the same thing. Let's go do it one more time for fun, or should I leave? Well, you should try it on your own. You should try just stopping the video and see if you can do it on your own. But then, you know, I can fill in for you. So I'm going to let the first of the orthogonal basis be the first vector, v1. Then I'm going to go find v2. Okay, so this is what I would call u1 and u2, right? So v1 will be my u2, so 4, negative 1, 2, subtract this vector here, 4, negative 1, 2, whoops, I can't erase on this thing, 4, negative 1, 2, times my vector 2, negative 5, 1, right? Those two are dotted with each other. I should say dot, not times. And then I'm going to take the dot product of this 2, negative 5, 1 with this 2, negative 5, 1 times this 2, negative 5, 1. Okay, so I get this 4, negative 1, 2 minus, so be careful with that subtract, right? So I get 8 plus 5 plus 2 all over 4 plus 25 plus 1 times this vector. So 4, negative 1, 2 minus, so this gives me 15 over 30. It's a 5, right? Okay. So then I get 4, negative 1, 2. And so this is a negative 1/2, right? So I'll keep the negative out here and I'll multiply the 1/2 in. So I get negative 5/2 and then a 1/2, right? Keeping the negative out there. There we go. Okay, so then subtracting those two. So I get 4 minus 1, so that gives me 3. Negative 1 plus 5/2. So that gives me a 3/2, and 2 minus 1/2, so that gives 2 minus 1/2 gives me a 3/2 as well. Okay, so there it is. So my two vectors, v1 comma v2, which are my orthogonal bases, are 2, negative 5, 1, comma 3, 3/2, 3/2. So it's not so obvious that the dot product is 0 like the other one, right? The dot product of these two for sure was 0. So we could go through and check it just to make sure you see. I want you to see that this is true. So 2, negative 5, 1 dotted with 3, whoops, 3, I keep doing the same thing, 3, 3/2, 3/2, right? Okay, so this gives me 3/2, I'm sorry, this gives me 6, 6, negative 5 times 3/2 gives me negative 15/2, and this is a 1 times a 3/2, so I get a positive 3/2. Is that really true? Let's see, so these two join together to give me a negative 12/2. Oh, look at that, it is 0. Okay. So now we get into the part where we're doing 3 vectors. So I want to find the orthogonal basis from 3 vectors. 1, 2, 3. All right, so I've given you the answers down here. So I wanted to make sure we got them all right, but let's make sure we understand the process. Again, let V1 be the first one. So there it is. So to find V2 will be the second vector, so 0, 1, 1, 1. Subtract off that vector dotted with the first one, 1, 1, 1, 1, and then the dot product of that V1 on the denominator, all multiplied times the V1. Okay, so 0, 1, 1, 1, and then take subtracting off, so multiplying this, I get 3 in the numerator. On the denominator, I can see I can get 4. So 1, 1, 1, 1. Okay, so I get 0 minus 3/4, so that's a 1/4. 1 minus 3/4, so that's a 1/4. Oh dear, what did I just say? 0 minus 3/4 is negative 3/4. Right there, right? Okay. 1 minus 3/4 is a 1/4. 1 minus 3/4 is a 1/4. And 1 minus 3/4 is a 1/4. Okay, so let me write that neater. So I get a negative 3/4 for the first one. 1/4, 1/4, 1/4. Okay, oh, and there it is right there. Okay, so since this is a vector that I'm creating for my basis, these are basis vectors. So remember, basis vectors, we're going to be taking linear combinations of these things, and that will make, they'll span and be linearly independent. I can create V2 prime, which is multiplying this by 4. This is just to make the computations easier as I move forward. Here we go. So now here comes the tricky part. So to find the third vector, to find the v sub 3, I'm going to take my x sub 3. So to find v sub 3, I'm going to take my x sub 3, which is the 0, 0, 1, 1 from above, right? And I'm going to be subtracting off. So here's where you have to be really careful with these parentheses. I'm going to be subtracting off the dot product, whoops, of this dotted with v1, which is 1, 1, 1, 1, divided by the dot product of the v1 with itself. And that's going to be all times the v1 vector. Plus, see guys, I've got this here, right? Plus, so I'm right there, plus the v3, which is the 0, 0, 1, 1, dotted with my v2 prime, this new vector here, right? And then I'm going to be on the denominator, I'll be taking the dot product of my v2 prime and then multiplying that times my v2 prime. Okay, that's all in the parentheses there. Okay, so here I have 0, 0, 1, 1, and I'm going to be subtracting off. So this dot product here I can see will give me 2, and the denominator will give me 4, 1, 1, 1, 1, plus, and see this dot product here will give me a 2, and the dot product on the denominator, 9, 12, right? And then times negative 3, 1, 1, 1. Okay. So then moving forward, so 0, 0, 1, 1. So now I'm going to distribute this negative sign through. So I get a negative 1/2. And then this give me a negative 1/6. Okay, so joining all those together, I get a 0, a negative 2/3, a 1/3, and a 1/3. So that's my V3. So again, we've got some not so pretty fractions. So I can make a V3 prime and take and multiply this vector by 3. So this V1, V2, and V3 is my orthogonal basis. And I'm not going to write them all down again. You can see them. But my orthogonal basis. Okay. So this one I am going to leave for you to do. So to find an orthogonal basis for the column space, what? For the column space of this matrix. So that means that this is the vector u1, this is the vector u2, and this is the vector u3. So I'm going to be, I'll just give you the answer. I want you to try to do it. So my orthogonal basis turned out to be, well, the first one's nice and easy, right? That's the first vector given. So 1, 3, 3, negative 1, comma, negative 3, 1, 1, 3. So hopefully you got that.